Hello, this is FlippedHarber for Algebra 2. In this video, we'll cover Section 4.5, Matrix Inverses and Solving Systems. When we talk about the inverse of a matrix, we're talking about another matrix that when multiplied with the original matrix, we get the identity matrix, which we signify with an I. Only square matrices have inverses, but not all square matrices have an inverse. This is going to be one of the few times where matrix multiplication is commutative. That means the order that we multiply them doesn't matter. If we take a matrix A and multiply by its inverse, it's the same as taking the inverse and multiplying by A. Either way, we're going to get the identity matrix I. Now, if we want to determine if two matrices are inverses, what we'll do is simply multiply them together and see what we get. So taking the rows from the first matrix and the columns from the second matrix, when we multiply together, we get a 2 by 2 identity matrix. Remember, an identity matrix is one that has 1's in the primary diagonal and 0's everywhere else. So 1, 0, 0, 1 is the identity matrix. So that shows that these two matrices are inverses. Now, there's a fairly easy way to find the inverse of a 2 by 2. It's going to involve finding the determinant of the 2 by 2. And then we make a minor change inside the matrix itself. You'll notice that if A equals A, B, C, D, the inverse is equal to 1 over the determinant of A. And then we flip the two numbers in the primary diagonal and change the signs on the numbers in the secondary diagonal. So let's find the inverse of this 2 by 2 matrix. First thing I need to do is find the determinant. So I do the primary multiplication, 2 times 4, minus 5 times 2. I switch the 2 and the 4, and I leave the 2 and the 5 in the same spot, but I change their signs. Now, what I get for 1 over the determinant is a negative 1/2, and I need to go ahead and multiply that scalar into the matrix. So here's my inverse matrix. So let's take a look at another inverse matrix. Again, we start by finding out what the determinant is, 1/2 times 12, minus 2 times 3. We switch the numbers in the primary diagonal. We leave the 3 and the 2 where they're at, but we change their sign. Now you might have already picked up here that there's going to be a problem. My determinant is 0, so when I take 1 divided by 0, that's a really major problem. And what that means is that this matrix does not have an inverse. So remember, only square matrices have inverses, but not every square matrix has an inverse. Whenever the determinant is 0, that matrix does not have an inverse. Now, we use this inverse matrix idea in order to solve a system of equations. And the first thing we need to do is change our system of equations into what's referred to as a matrix equation. And it's always made up of 3 matrices. The first one here in the blue is what we refer to as the coefficient matrix. Now we use the coefficient matrix in Kramer's rule, so that should look fairly familiar. Our second matrix is our variable matrix, and it always has x in the first row, y in the second row. If this were a 3 by 3, which we're not going to mess with right now, it would be x, y, and z, all in one column. Now, those two matrices multiplied together equals another 2 by 1 matrix that we call our constant matrix, which is literally just the constants from the other side of the system of equations. Now, we can use this matrix equation to solve for x and y. So the way that we solve for a matrix equation is we have to multiply by the inverse. Now, where that inverse goes in the equation is important. You'll notice that A inverse is in the front on the left side. That's so that it's multiplying the matrix A. since A inverse is in the front on the left side, it needs to be in the front on the right side as well. So where you put that A inverse is important. It has to be in the front. Now, when we take A inverse times A, that's going to give us the identity matrix. That means that whatever numbers we get on the right side of the equation, we'll have our top number in that resultant is our x value, the bottom number is our y value. So let's try this with this system of equations. The first thing we need to do is make our matrix equation. Remember, the first matrix is just the coefficient matrix, the 5, 3, 2, and 2. Our second matrix is in a column, x, y. And then on the other side is just our two constants, negative 12, negative 4. So the whole top row looks like it's basically the top equation. The whole bottom row looks like it comes from the second equation, and that's true. Now the next thing we need to do is find the inverse of our coefficient matrix. Now, I talked about how to find the inverse matrix, so I went ahead and just saved us a whole lot of hassle. Here's the inverse matrix. We'll multiply by that inverse matrix in the front on both sides of the equation. Now, do not spend your time working on the left side of the equation. As long as you found the inverse properly, there's absolutely no work to do on the left side of the equation. When we take our inverse matrix times our coefficient matrix, it's I. Don't spend your work there. Spend your time doing the multiplication on the right side of the equation. Take the 1/2 times negative 12 plus negative 3/4 times 4. Then negative 1/2 times 12 plus 5/4 times the negative 4. Again, on the left side, you just have the identity matrix. Don't spend your time there. Spend your time multiplying on the other side, and we get negative 3, 1. Now we can literally just read off our answers. The x is on top, the y is on bottom. So in this case, the solution to the system of equations is negative 3, 1. Okay, so all that's really left to do is to practice this. You've learned how to find inverse matrices already. Now we need to spend some time practicing this process to solve a system of equations. All right, I'll see you in class, and I'll see you online.